Simon Murphy from Sydney will be talking about confirming compact stellar remnants found by pulsation timing using Keck HIRES. And you're off.
It does help if you unmute, doesn't it? Thanks everyone for sticking around for my talk at the end of the session, and thanks to the organizers for squeezing me in with my difficult time zone constraints on the other side of the Pacific. There are around 10 to the 8 stellar mass black holes and around 10 times more neutron stars expected in the Milky Way. So the big question is, how can we find stellar mass black holes or neutron stars, which together I'm calling compact remnants? So the high mass stars that will eventually become compact remnants are almost always found in binary systems. So this plot here shows the fraction of stars in binary systems with mass ratios greater than 0.1 as a function of orbital period for a variety of different stellar spectral types. And the stars that will eventually become compact remnants, so black holes, neutron stars, they're very often found in binary systems. And in fact, the binary mass ratio suggests that many of their companions should be intermediate mass stars. So by studying the orbits of intermediate mass stars, we can hopefully find massive compact remnants. But binary orbits for intermediate mass stars are difficult. These stars rotate rapidly, often with V sin I exceeding 100 kilometers per second. So the spectral lines are very broad. And these stars also pulsate both radially and non-radially with pulsation velocities exceeding 1 kilometer per second. And this has two effects. It shifts the line profiles, and it also distorts the shape of the line profiles. So all of these things make radial velocities difficult to determine for intermediate mass stars. So the stars that I'm particularly going to talk about today are called delta Scuti stars. They are located at the intersection of the classical instability strip and the main sequence. And they have masses between about 1.5 and 2.5 solar masses, and most of them are main sequence objects. Now you may already be familiar with pulsation timing and the light travel time effect, but here's a quick rundown just in case. Imagine you have two stars, they're in a binary system together, they're orbiting each other, and traditionally you would detect this by Doppler shifts of their spectrum, and you detect this with some telescope on the ground. I'm sorry that I didn't have a little globe that showed Hawaii. So you detect this via the Doppler shifts, but the same orbit also has a light travel time across it. It has a finite size. And if you study the pulsations of the stars at two different points in the star's orbits, there'll be a path length difference between them. And that path length difference gives you a shift in the pulsation phase. And it's that shift in the pulsation phase that we're looking to detect. We don't detect that with ground-based telescopes. We use white light photometry, usually from the Kepler Space Telescope, because it has a nice 4 years of continuous observations. And the additional requirement that we have is that the star must have coherent pulsations, meaning the phases are intrinsically stable on timescales longer than the orbital period. So when you extract these time delays, you essentially end up with something that looks a little bit like a radial velocity curve. If you've worked on eclipse timing variations, you'll be familiar with this type of curve already. And from this curve, we extract the same orbital parameters that we get from the radial velocity method. In fact, the radial velocity is just the time derivative of the time delay multiplied by the speed of light. So the radial velocity method has a sensitivity that scales as orbital period to the -1/3, whereas pulsation timing has a sensitivity that goes as period to the +2/3. So the methods are very complementary with each other. There are around 2,200 delta Scuti pulsators observed by Kepler, and from those we found 317 PB1s. This was in analogy to the SB1s of spectroscopy, the single line binaries. And these were published in a catalogue of 2018, and they give us a large homogeneous sample on which to do some statistics. And one statistic that we might look at is the logarithm of the binary mass function. So in this plot, stars on the systems on the right-hand side have high mass functions, meaning high mass companions, and on the left we have the low mass companions. So in this project, we decided to observe the stars with high mass functions with Keck HIRES, and that's the sample shown in the orange histogram. So our method to find these compact remnants goes like this. If the high mass companion is a massive main sequence star, it's going to be bright. It's going to be very luminous. So it should show up in the Keck spectrum. And the spectrum should essentially be double-lined, an SB2. But if the spectrum is SB1, so single-lined, and the RV curve corresponds to the pulsating star's orbit, then the companion has to be a compact remnant. And this is an example that I'm showing at the bottom. So we have the time delays, which are the black data points with the red fit, and the radial velocities, which are orange data points with the blue fit. And the fit here is a joint fit that calculates the chi-squared of the combined data sets. And it's important to emphasize here that the CPSQ is really essential for adequate phase sampling of these radial velocity curves. So we can compute a minimum dynamic mass using these curves, and if it's greater than 1.4 solar masses, the companion can't be a white dwarf. So the compact remnant is a black hole or a neutron star. There's another thing that is essential to our success here, and that's what we call triple shots, or in other words, how to overcome pulsation velocities greater than a kilometer per second on 1 hour timescales. So here we have 3 spectra that were taken 50 to 60 minutes apart, and you can see distortions to the pulsation line profiles. But if we co-add those spectra, then we essentially iron out those distortions and we can extract reliable radial velocities. This is really important to make sure that any residuals to our single star fit to the spectrum are actually residuals that belong to a companion rather than being the result of pulsational distortion. But rapid rotators are still tricky. Here's a star with V sin I of 200 kilometers per second in the same spectral region. The line center does move between those spectra taken 10 minutes apart, but it's really hard to see or to measure directly. So it's not a perfect art form quite yet. This is my last slide. We've observed 47 systems so far, of which 40 have been analyzed. 32 have turned out to be SB2s or SB3s. So it turns out that triple systems are common false positives where we end up with 2 low mass companions rather than 1 high mass companion. 5 systems are maybe SB1s, but the pulsational distortions are difficult to disentangle for those rapid rotators. And then we have 3 systems that are definite SB1s, and we find that their minimum masses are close to 1.4 solar masses, and we're still refining them. I'd like to thank my collaborators on this project at this point, and thank you all for listening.
Okay, thank you very much. I don't see any questions online. We're getting close to the end of the day. I guess one of the questions I had is, you know, you just explored one small corner of that distribution. You know, is there a science case that you'd like to do where you go to the other end of that distribution? What would it require to do that? Is it greater PRV sensitivity, precision, which we might get with the KPF instrument? Is it going fainter? What are the plans for your future work?
That's a really good question. As I mentioned, the sensitivity of this method scales as orbital period to the +2/3. So we're actually sensitive to planetary mass companions if the orbital period is very long. The problem is that at long periods, we can't really get precise enough radial velocities for these rapid rotators to confirm the planets with radial velocities. But this method has turned up 1 planet so far by pulsation timing. That was a planet in an orbital period of about 800 days.
Okay, well, thank you. I guess then if there's no, let's see, here's one question here from Jessica Liu. Is it unexpected that there were no or only very few black holes or neutron stars?
I haven't actually done the calculation to work out how many we expect from this sample. I wouldn't have expected to find many. I wouldn't have expected to find, say, more than 10. But I don't know if 3 is around the number that we expect, but thank you for the question.
Okay, I think at that point we'll call this session closed. It's been very informative and certainly some good science in the last talk.